All right. Thank you all for joining me this afternoon for my talk on Apache Flink. So it's going to be a deep dive on the features of Apache Flink and how we process batch and stream data in one engine. My name is Robert Metzger. I'm a committer at the Apache Flink project. I'm employed at Data Artisans, a Berlin-based startup which is developing Flink in the open. Presenter is not working. Okay, so before I explain to you what Apache Flink is, I would first like to take a look back into the recent history of the project. So not a long time ago, in April 2014, the project was accepted at the Apache Incubator. So this is the way how new Apache projects get there. And back then, the stack of the system was rather small. So it consisted basically of the core runtime, some deployment options, and a batch API that we exposed on top of it. Only 7 months afterwards, the project was graduating as a top-level project of the Apache Software Foundation. And today, if you look at the system stack, it has grown a lot. So the runtime has been extended by many more options. And also you can see that we created a lot of releases, and we are about to release the 0.9 version of Flink. So what is Apache Flink? So the very core of the Apache Flink platform is the streaming data flow runtime. So that's the engine that is processing the data in parallel in a distributed fashion. On top of that, we have two main programming abstractions. So there is the dataset API for batch processing, and there is a data stream API for real-time stream processing. Both these APIs are exposed in the Java and the Scala programming language. On top of these two abstractions, we've built various higher level abstractions. So there is, for example, a MapReduce compatibility layer, which allows you to execute existing map and reduce user-defined functions, but also Hadoop input formats and output formats. And also we support all the file systems implemented by Hadoop. Then there is the table API, which gives you a logical view of your data. So there you can do SQL-style operations like filtering and so on. And in the behind the scenes, we are generating code for you for efficient execution. Then there is the Jelly API, which is a graph processing API. So it contains utilities for analyzing huge graphs in Flink. We've also recently started the Flink machine learning library, which allows you to do machine learning at scale. So the green boxes are basically projects that are contained inside the Apache Flink platform. But there are also other projects like the Google Dataflow Runner, which allows you to run batch jobs implemented against Google's Dataflow API in Flink. So you can develop your Dataflow programs on-premise, you can test them locally, and for running them and on Google's platform, you can take the same code and run it there. There's also support for Apache MRQL, and we're working on a layer for supporting cascading as well. For the streaming side, we also have support for the table API. Then the Apache Samoa project has support for machine learning on streams, so you can update models as the data comes in. And we are also working on the data flow support for the stream API of Flink. Yeah, I forgot to mention that we are also having support for Zeppelin now for the batch API. So you can also do this notebook-style interactive querying against Flink. So these are the APIs and systems that we are exposing on top of the system. And there are also various deployment options for Flink. So there is the so-called local runner, which allows you to run Flink in one JVM. So it's starting all the services that Flink contains in one JVM, which allows you to run Flink on your laptop or on your machine. It also allows you to run it from the IDE and debug through your program. Then we have the remote option, which is kind of a bare metal installation. It's like installing Hadoop on your cluster. You just unzip a file, start it. Then there is support for Hadoop Yarn, so you can deploy Flink with 4 commands on your Yarn cluster, which is a very easy way to try it out, also on Amazon or Google. Then we have support for Apache TAS, so you can also deploy Flink using TAS in the Yarn cluster. This allows you to do very fine-grained resource control. And then there is an embedded option, which is basically bypassing the entire runtime, and it allows you to execute Flink basically in one thread. So how can you make use of the system? This is a little example that shows you that, so this program here is written in the Flink Scala API, and it shows you how the program goes through the various stages of the Flink system until it's finally executed. So the first step is that the system is, this Flink client is doing a type extraction on that program. So it analyzes what types you're using for your user-defined functions to generate serializers from these types and to execute efficiently on your data. Then we'll also run a cost-based optimizer on your program. So we'll automatically deduct the best execution strategy, both for the execution in the cluster, like how the data is repartitioned and so on, and also for how we execute the individual operators, for example, how we execute and join. And the outcome of this pre-flight phase, which will also check that your program is valid and so on, is a data flow graph. So this graph is an independent representation of Flink programs that the engine can execute. So when you program against the streaming or the batch API, they all end up with this data flow graph. And then this graph is submitted to the master, which will then distribute work to the worker nodes and also will maintain metadata about your job. So Flink has a layered architecture where you can plug in or change parts of it. For example, this test integration changes, like replaces the lower layers of Flink and adds the test engine there. All right. So Apache Flink is a general purpose data processing system which has built-in native support for a wide array of use cases. So you can run streaming topologies on it with very low latency. You can execute huge batch jobs which will run for hours, processing tera and petabytes of data with very good resource utilization. You can do machine learning at scale. We have built-in capabilities for executing iterative algorithms in the system. And you can also do graph analysis with Flink. We've also built-in support in the engine to do that very efficiently. So there are 2 questions now. How can you build an engine that can support all these use cases, what we call natively, and what does this term native mean? So it means that we have in our engine built-in entry path to tell the system what you want to do. So when you want to do an iterative algorithm, you can tell the system that you're going to execute or that you want to execute iterations on it. You can also tell the system, I'm now going to do streaming. I want to have this fault tolerance strategy. If you don't have that, if your system doesn't support that, you have, for example, when you want to execute iterative algorithms that you need for machine learning, you need to treat the system basically as a black box and work around the limitations. So what you would do, for example, with Hadoop is that you write a job that is doing the executing a step of your iteration. So for example, training a model, and then you run this job over and over again. So this is the system doesn't know what it's doing. You're just working around the limitations of the system. Another case of not native support for a feature or a use case is stream processing. So what you can do when you only have a batch processing system at hand is that you simulate a stream processor. So what you're doing is you take the input stream and create small data sets out of it, and then you use these data sets to submit batch jobs. From the outside world, it looks like you're doing real-time stream processing, but the system, the batch system, actually doesn't know that it's doing stream processing. So I hope you now understood what we mean by native workload support. And now there's obviously the question, how can an engine support all these different workloads in one engine? And for that, we have 5 cornerstones in our system. So the first is that we execute everything as streams. So the system has a push model. So all the operators are pushing data to the following operator. For stream processing, this means that there's no latency, there's no waiting. We can just push elements as they come to the subsequent operator. Sometimes we need to block for batch execution, but this is treated inside the operators. Then we have special code path for batch programs. So when you do a batch program on our pipeline runtime, you can do further optimizations because you know that the data set is finite. You know that the incoming data will stop at some point. And when we know that we are executing a batch program on Flink, we can do a different form of fault tolerance, and we can also do the automated job optimization using the optimizer. Then the system has built-in support for executing these iterative algorithms that I've just shown you, which are used for machine learning. The system also allows you to have mutable state inside your jobs. It's a very defined way, so we can do this in parallel, but it still allows you to execute particular graph processing algorithms very efficiently. And since we are running on the JVM, like most of the big data projects, we need to make sure that we are not suffering from huge garbage collections or that the garbage collector is slowing us down. So we want to take control of the memory. And for that, we manage the memory ourselves inside the JVM. For the remainder of the talk, I'm going to talk about these 4 use cases and explain to you what features we have built into the system and how we support these on our pipeline runtime. So the first use case is stream data processing. I'll just give you 3 slides that show the main features of it, because we'll have a full talk on that tomorrow in the Grand Ballroom. And there you can learn how we do stream processing in Flink. So as I said, Flink has a pipelined engine, which means that the operators are running in parallel, sending or pushing data forward. So in this example, you have a data source, which is connected to a tokenizer, which is splitting the elements. And then you have a shuffle for redistributing the records in the cluster to this green window operator. And the thing is that all these operators are running in parallel, and they push the elements as they come into the system immediately. So there's no synchronization, there's no waiting. And also the shuffle there, so the redistribution maybe based on a hash function, is happening in real, like immediately. There's no waiting. Another great feature of the Flink streaming is that we have very accessible APIs. So it feels a lot like programming Java, even though you are actually programming on very big data sets or on data streams. So the upper code is the word count implementation in Flink's batch API. And there you can see that you have all the primitive operators like flat map, map, group by, and so on. And the lower part contains the word count implementation for Flink streaming. And there you can see it looks pretty much the same. So there, it is very accessible to operate on streams. The only thing you have to understand is that the data stream is like sending you or giving you data forever. So it's a very nice way to transition from batch processing into stream processing. Since you cannot really group on an infinite data stream, you have to define windows in stream processing. And for that, there is this window operator that allows you to specify in various ways, for example, by using a delta or by using time, how big the window is and how many elements are going in there and when they are processed. So in this example, the window has a size of 5 seconds, and every second we create a word count for all the elements which are currently in the window. And the last feature of Flink streaming is how we do fault tolerance and how we guarantee exactly once processing in a very efficient way. So what we do is we implement a variant of the Jandy-Lamport algorithm for asynchronous checkpoints. So what the system is doing, it is periodically, let's say every 5 seconds, creating checkpoint barriers at the sources. And these are walking through the system together with the data stream. So they are aligned with the incoming records. And as soon as a barrier reaches an operator, the operator will back up its internal state. So users can, inside user-defined functions, inside a mapper, for example, that contains a counter, can register that state. So the system knows there is a counter inside the operation, and as soon as a barrier reaches that operation, the system will back up the state. As soon as all the barriers reach the sinks, we know for sure that the state is backed up. And in case of an error, we can restore to that state and continue processing. So by this, we have a very efficient way of providing you low latency while having fault tolerance, because we are creating batches next to the data. Then there is the support for regular batch processing in Flink. This is the API that we had for a very long time, that we were exposing for a very long time. And for executing batch on a streaming engine, you might wonder if that's actually possible. But other systems like Cloudera Impala are also doing this, so they are also relying on a pipelined runtime. So as an example, imagine you have a batch job that reads a file from HDFS and then sends it to 2 operators. So the first one is a filter and the other one is a map. And so we have 2 outputs of that job. And the thing is, executing this on Flink will cause the system to never materialize to disk or to memory. So we read the file from HDFS, and this reader, this data source, is sending the elements from that file to the filter and the map operation. And the filter then is sending it to the map. So the data is never materialized anywhere. It's always flowing, and causes a very, very good resource utilization. But yeah, as I said in the beginning, it's a very simple example. So as soon as you have operations like join or reduce, you can still execute this with a pipelined engine. So in this case, you have a data source with some small data, and there are 4 operations which consume the data from that. So there are 4 map operators which will process the elements in parallel, and we will also stream the data from this data source to the join operator. So the join operator is creating the build side of the join, and once the build side has been completely built, so once the data source has been completely consumed, the second source will start streaming elements to the probe side. And the interesting thing is that the join operator will be executed in parallel with the map operation. So they are both running together. So for processing batch, you have a few requirements. So you want to get your data processed as fast as possible. You want to use all the resources that you have. And for that, we have this automated job optimizer, which will come up with the best execution strategy. And we have built-in memory management. So the system is not relying on the JVM heap, we're doing it ourselves. Also, you want to have robust processing, so you don't want your job that has been running for 10 hours to fail in the last hour. Again, we achieve this by fault tolerance and memory management. So Flink features a cost-based optimizer inside a system where you can program the queries yourself. So we can still do optimizations on that. So we can, for example, select on the data shipping strategy. So you can, for example, repartition your data for a join, but you can also broadcast it when the data is small enough. And the optimizer is going to take like samples or information from the data sources to estimate how big the data is going to be, and then it can decide which join strategy to execute. It will also decide on the local execution strategy, for example, when it knows that two subsequent operations can reuse the sorting property of the data, then we can skip the second sorting. Also for the iterative algorithms in Flink, we are able to like move out certain processing steps out of the loop. And the optimization happens in this pre-flight phase that I've mentioned earlier. I'll skip this due to the time. So how do we do managed memory in Flink? As I said, you need this for avoiding out-of-memory exceptions and also for avoiding large garbage collection stalls. So you don't want the JVM to be unresponsive for maybe even many minutes when you have very big heap sizes. So what we do is we allocate byte arrays up front. So when you start a Flink worker, they'll allocate 70% of the available heap space that we'll manage ourselves. So the garbage collector doesn't need to take care of that. And then the internal operators will put user data into this managed memory to perform sorting operations or joining operations. But now you might wonder, how do we do these sorting or hashing operations on top of our own managed memory? And what we are doing, we have our own serialization stack, on our own serialization framework, which is initialized during the pre-flight phase when you submit a Flink job. And there we have serializers that allow the operators like a join or a sort operation to turn the elements from the heap into our own managed memory. Also, the serializers allow us to do, for example, comparisons on binary data. So we don't always need to deserialize everything when we do a comparison. Also, the operators like the sort is able to destage to disk. So if the memory is not sufficient, the system is able to put parts of your data from memory to disk. So by default, Flink is operating in memory, but it sometimes needs to use local disks, like operating systems to swapping. We've also tested that behavior. So in this experiment, we had the hash join executed locally, and the blue bars show you the join that the join is running only in memory, and then the orange bars show you the performance impact of going out of memory, so putting part of your data out of core. So you see it's destaging very nicely. You don't have a big penalty for going out of memory. The next use case are machine learning algorithms. As I said earlier, for executing those, you need to have support for iterations, because you go over the data over and over again to, for example, train a model. And with many systems like Hadoop, you would work around the system. So you just resubmit your job over and over again. In Flink, you don't need to do that. You can tell the system directly, hey, look, I'm executing an iteration. There is like some pseudocode how the system is executing them. So you basically give them initial state, and then you give a step function, which can be an arbitrary data flow, so you can perform a lot of operations there, like joining, grouping, and so on. And in the end, you'll have a final result. So you can specify in different ways how the system knows when an iteration is over. We also tested this, so we factorized a matrix with 28 billion ratings, and we created a rating matrix out of that. And in this experiment, so I think the input data was like 1 terabyte, but the intermediate results, so the data that is being created while executing this job, is actually much larger. So it's many more terabytes. And on the medium instances, on Google Compute Engine, it took us 13 hours using bigger machines with 100 gigabytes of memory. We could bring down the runtime of that job to 5 hours. So you are able to update your recommendation model multiple times a day. So you can serve your users very up-to-date, very fresh recommendations. And the 28 billion graph matrix is pretty big. So I think it matches what many users use in the industry. If you're now excited about this, and if you want to try it out yourself or use machine learning algorithms on Flink, we have a library started recently, Flink ML. It will provide you a complete tools chain of stuff that you need for doing machine learning. So we are following this scikit-learn style pipelining approach where you can plug in different learners and assemble them as you want. But we'll also provide utilities, for example, for data pre-processing, also for loading your data from various formats. And yeah, we are starting to add more and more algorithms to it. For example, this ALS algorithm that I've just shown is contained in the library. We've also support vector machines there, and we'll add more to this. If you want to do machine learning on streams, you can use the Apache Some More project, which is in the Apache incubator. So yeah, but we are also planning to add support for machine learning on streams to our system. Another use case is graph analysis. So you want to process like Twitter follower relationships or other graphs like the web. And when you look closer at those algorithms, you'll realize that the number of elements updated with each iteration usually goes down rapidly. For example, for a label propagation algorithm where you send labels through a graph, you'll see that the number of elements inside that graph which are updated goes down rapidly. Without having this support for what we call delta iterations, you would process the entire graph in each iteration. But Flink allows you with this delta iteration operation to make the system aware which parts of your data, which parts of the graph still need further processing. And by that, the system is able to put the available processing power onto those parts of the graph that are still not converged. So, and to do that, we relax a bit the assumption of batch processing. So we make the data a bit immutable, but very, very limited and very well defined. So we have this solution set, which is a hash map, which is locally on each machine, where you can put the finished parts of your graph into. We've also tested this. In this example, we've implemented the PageRank algorithm. There you can see that for executing 61 iterations with the regular iteration abstractions in Flink, we needed roughly 20 minutes. But implementing the same algorithm with delta iterations, we brought it down to 8 minutes. Because the system is able to put the processing power onto those parts that still need it. If you want to learn how we did it, there's a great blog post linked in the slides that explain how we did it. If you're now interested in graph processing, we also have a library for that. It's called Jelly. Jelly provides you data types and abstractions to represent your graph in your program. You can then perform transformations on that, like mapping or checking for subgraphs, merging graphs, stuff like that. You can also mutate the graph, so you can add elements or remove. You can also execute Pregel-style vertex-centric iterations on top of that. So it's this BSP processing model where you send messages to the nodes so they communicate to each other. And we also provide a set of libraries in there that you can use to execute known algorithms on your data. Both Jelly and FlinkML will be available in Flink 0.9. So we have a milestone or preview release available, but we are currently preparing the 0.9 release in the community. Both libraries are under heavy development, so we'll add more stuff. But I think they are already in a shape that you can use them in production or to try them out. They both integrate with the regular abstractions of Flink, so you can pre-process the data as needed. You can do all the standard transformations that you have in the Flink APIs, and you can also use the results as you want. I think both projects are a great way to start contributing to Flink if you're interested in that. If you're interested in connecting with the Flink communities, there are a few ways, and I'm really excited to see that there are so many new meetups popping up. So there is the San Francisco Spark and Friends meetup, where we will present Flink on June 16 in San Francisco. We've also started the Bay Area Flink meetup. We'll also have great talks there. And yeah, there are other meetup groups all over the world. Another way to connect with the Flink community is the Flink Forward conference. It will happen in Berlin. It's a 2-day conference where we'll also have workshops, and it's a great opportunity to meet the developers and learn what's going on in the community. Yeah, and if you're not living close to Meetup, you can always go to our website, connect with our community, write to the mailing lists, and follow us on Twitter. That's it. All right, and now I'm open for questions.
Did you compare performance of Spark streaming with Flink streaming?
So the question is whether we compared the performance between Flink streaming and Spark streaming. We do internally some testing sometimes for features, but yeah, we are not sharing these experiments. But I would really recommend to try out Flink. So it's as I've said, it has great APIs for stream processing, and also it contains a lot of cool stuff like the pipelined execution and the fault tolerance mechanisms for exactly once processing. So I would really recommend to try out Flink streaming. More questions? Yeah?
Can you elaborate on fault tolerance in the batch context?
The question is how we provide fault tolerance in the batch APIs or in the batch system. So for batch, we right now have a very coarse-grained fault tolerance. So the system will restart the job when it fails for a reason. But we are currently working on adding a much more fine-grained fault tolerance into the system. So we are actually going to provide a way to tell the system to execute parts of your job in a batched fashion. So you're not going to stream everything, and we are going to create checkpoints inside this data flow graph. And if an operator fails, it will restart from that checkpoint or from the last checkpoint. So we will implement something which is similar to lineage. So it's going to backtrack to the last available result, or it's going to recompute from the source or wherever the data came from.
Can you read from Kafka?
The question is whether we can read from Kafka. Yes. So Flink streaming supports Kafka, and Flink streaming is also using the internal mechanisms of keeping the offsets within Zookeeper. So in case something fails, the system knows where the offsets of the partitions. So it's able to reread where it left off when the job failed, for example. So it has support for Kafka. Yeah. Yes?
Will the join be support for the streaming data processing?
The question is whether stream data processing also supports join. The answer is yes. You have to define a window, but within the window you can perform joins. The issue is you cannot perform a join on infinite data. Therefore, you create a window, and then inside this window, all the elements are considered for the join.
Can the result be updated after that? Since data come a little bit late for now.
The question is whether the result can be updated concurrently, so the result of the join.
No, after the join. Maybe you want to join based on some timestamp, the event timestamp.
Mm-hmm.
So you already made a code previously about the result for this window.
Mm-hmm.
Then during the next window, the data for previous timestamp arrive.
Mm-hmm.
So can the Flink to update the previous result?
No. So the question is whether Flink can update like results from previous windows. Yeah, but no, that's not possible. But we can discuss offline if you want. Yeah?
Can you say a few words around Spark versus Flink, when to use what?
Okay, so the question is when to use Spark, when to use Flink. Yeah, so as I, yeah, oh, sorry. Huh? So was that the question?
The question is Spark compared to Flink, when to use what are advantages?
Okay, it's very hard to answer. I would say use whatever fits the best for you, for your use case. I would certainly recommend you to try out Flink. I mean, it has great capabilities for batch processing. For example, the optimizer allows you to automatically deduct the best execution strategy, so you don't have to manually think about partitioning or join execution strategies. So you don't have to think about your data when you write your job. It is taken care of by the system. And the stream processing features of Flink are also very good because you achieve very low latency and you still have the fault tolerance guarantees.
How about the Storm and the Flink? How can you hook up together?
So the question is whether you can use Storm and Flink together, or you can reuse existing implementations from Storm. So there is a Storm compatibility layer, which is currently in pending pull request, but we will merge this. So you can reuse existing implementations against the Storm API on top of Flink streaming. Yes. Yes?
Is it possible to share code between like batch and streaming implementation?
Yes. So the question is whether you are able to stream code from a Flink streaming job and a Flink batch job. And they are both using the same interfaces. So if you have, for example, a flat map implementation, you can just reuse the same function. So the main difference basically is that you don't write data set, but data stream. But then you can put the same user-defined functions there. Yes?
Could you speak to the maturity of the Python bindings, and or specifically, are you planning on supporting CPython or just Python?
So the question is how we support Python. So what? So I'm not 100% sure how the implementation exactly works, but Flink has a Python API for batch. It's relying on the Java API, and it's basically bringing up a Python process and then streaming the data from the Java process to the Python. There you can do your processing, and then you stream back the data. So right now there's only support for the batch API. There's no support for streaming. And for machine learning, I mean, there are a lot of great libraries for doing machine learning in Python. Yeah. But we can also expose our internal like machine learning or graph processing APIs there. Yeah. Yes? The question is whether Flink has an interactive shell. Yes, we do. So in the upcoming 0.9 release, there will also be an interactive Scala shell where you can interactively explore your data. Yeah?
What's the interactive shell in now?
What do you mean?
What language is the interactive shell in now? Or is it in DSL? Or?
The interactive shell is Scala. So you just write Scala code there. So before 0.9, we didn't have an interactive shell, so we just added it. Yeah. All right. If you have more questions, please approach me or Kostas here. Thank you.